Welcome to This Explainer. Today, we're diving into a fascinating, really high-stakes electrical mechanism that's honestly silently operating all around you right now. It's this invisible piece of engineering that quite literally prevents our critical infrastructure from just, well, completely collapsing. We're talking about the Latching Control Circuit. If you've ever wondered how massive industrial systems, manufacturing plants, or even those huge data centers that run the entire internet stay online when the computer systems glitch out, you're definitely in the right place. We're going to break it all down step by step and reveal the absolute hidden hero of modern automation.
So here's our roadmap. First up, the momentary switch problem. Then, the circuit with a memory. After that, electrical versus mechanical latching. And finally, the data center failsafe. Let's just jump right in.
All right, part one, the momentary switch problem.
To really get why this matters, think about a super standard, everyday object, the classic doorbell. A doorbell uses what engineers call a momentary switch. You walk up, press the button, the electrical circuit closes, and the bell rings inside. But what happens the exact millisecond you let go? A tiny mechanical spring physically pushes the button back out. The circuit opens, the electricity stops, and the bell goes totally silent. It only works for the exact moment you're physically pushing it. Now imagine trying to run a massive 500 horsepower industrial water pump at a city utility plant using that exact same doorbell logic. If we used a momentary switch there, you'd literally have to hire someone to just stand there and hold the button down with their finger forever. I mean, if the guy sneezes, the whole city's water supply shuts down. It's completely absurd, right? We desperately need a way for a machine to stay on after just a single press.
Which brings us perfectly to part two, the circuit with a memory, the latching solution.
Enter the Latching Control Circuit. What's so cool about this concept, sometimes called self-holding or lock-in, is that it maintains its output state even after that original input trigger is completely gone. But simply, it's an electrical circuit with a literal memory. Once you tell the circuit to turn on with just a quick momentary press, it actually remembers that command. It locks the electrical path closed and stays on indefinitely. It absolutely will not turn off until it gets a completely separate, explicit command telling it to turn off. Boom, doorbell problem solved.
Okay, part three, electrical versus mechanical latching.
Let's break down the first way engineers do this, the electrical approach. I'm going to carefully walk you through these 5 exact stages, because this is where the real magic happens. So, step 1, the system is idle. Nothing's happening, zero current is flowing. Step 2 is the trigger. An operator presses the start button, electricity rushes in, and it energizes a relay coil. Now, step 3, this is the critical moment, the latch. The second that relay coil gets energized, it acts just like a magnet and pulls all of its physical metal contacts closed. And here's the absolute genius part. Engineers wire one of those contacts in a parallel loop right around the start button. So in step 4, the release, when the operator lets go of the start button and it pops open, the machine actually doesn't stop. Why? Because the electricity found a new path. It just keeps flowing through that parallel loop the relay just closed. The relay is cleverly keeping itself alive. It's self-holding. Finally, step 5, to stop the whole shebang, you press a totally separate stop button. That physically breaks the main power loop, drops the electricity, opens the contacts, and breaks the latch.
So, building on that, let's compare our two options. We just looked at the electrical approach, which uses that really clever continuous wiring loop to keep a coil energized. But there's another way, the mechanical approach. Instead of using electrical logic, a mechanical latching relay uses physical hardware to remember its state. It's a two-coil system. When a brief pulse of electricity hits the first coil, the set coil, an internal physical mechanism, or sometimes even a permanent magnet, physically flips a switch arm to the on position and physically locks it there. And this brilliantly highlights a huge difference. Once it's mechanically locked, you can completely cut all the power to the panel, and that switch, it stays locked on forever. It requires literally zero electricity to maintain its memory. It's only going to flip back off when you send a brand new electrical pulse to the second coil, the reset coil.
And now for part 4, the data center failsafe. Let's look at the massive real-world stakes here.
Imagine a gigantic data center processing millions of global financial transactions every single second. These massive facilities are cooled by giant chilled water pumps, and those pumps are controlled by a central computer called a Building Management System, or BMS. The BMS sends out a 24-volt direct current signal to tell the pumps what to do. But ask yourself a genuinely terrifying question. What happens if that central command computer just dies? What if there's a software glitch, the network freezes, or there's a localized power failure, and that 24-volt signal instantly drops to 0 volts?
Well, if engineers design the facility using standard, non-latching circuits, that nightmare scenario becomes reality. The exact second the computer crashes and the voltage drops to zero, the pump's contactor instantly opens. Those massive industrial water pumps just grind to a halt. Thousands of gallons of chilled water stop flowing. Without that cooling, the ambient temperature in the data hall spikes immediately. Within a matter of minutes, millions of dollars of server hardware would literally start melting down. Data's lost, websites go totally dark, financial networks crash. And all of that just because a computer froze.
Now, let's walk through how they actually protect against this. In step 1, the central computer doesn't actually send a continuous signal. It just sends a quick, momentary pulse saying, run. In step 2, the local hardware at the pump gets that pulse and latches the command, locking it in mechanically or electrically. Now, step 3, the central computer crashes. The network is completely dead. But look at step 4. Because the command was latched locally in the hardware itself, the pump completely ignores the dead network. It just keeps running blindly. This local hardware insurance keeps the cooling water flowing and saves the servers, buying incredibly valuable time for the facility engineers to sprint to the room, figure out the fault, and manually override the equipment.
So let's summarize the massive technical wins we've uncovered. First, power efficiency. Especially with those mechanical latching relays, they don't need a continuous supply of electricity to stay on, which drastically cuts down the heat generated inside those crowded control panels. Second, status retention. If a facility loses power completely, a mechanically latched circuit doesn't forget what it was doing. The millisecond power comes back, it's instantly exactly where it was before the blackout, holding critical valves open or closed without waiting for some slow central computer to boot up. And finally, decoupled control safety. Latching circuits brilliantly separate the vulnerable software command system from the physical hardware execution system. It is basically the ultimate layer of hardware insurance.
It's honestly amazing to think that such a simple concept, literally just giving a circuit a memory, is the exact thing standing between a smoothly running internet and a total, catastrophic meltdown. The latching control circuit truly is the hidden hero of automation. Which leaves us with one final provocative question to ponder today. As our technology gets more and more complex and we become more reliant on fragile software, what other hidden hardware fail-safes are silently keeping our modern digital world from collapsing right now? Keep questioning the infrastructure around you. Thanks so much for joining me for this explainer, and I'll catch you next time.